Good morning, friends. In this lecture, we will see electrical analogy for the heat conduction. Now, main question is that why electrical analogy is needed. Now, in previous lecture, we see that by using Fourier's law, we can calculate the rate of heat flow. So that is Q is equals to, we are having Q is equals to Ka by B to bracket T1 minus T2. Okay, so this formula can be useful when we are having the single wall. If we are having one wall, something like that. If we are having wall something like that, and here we are having thickness B, then we can easily calculate the value of Q by using this formula. But normally walls are made by the different materials. Okay, and these are the wall are nothing but the composite walls. So composite wall means what? The wall made by the different materials. For example, in our home we are having wall which is made by the central layer brick, and around both the sides we are having the plaster layer. So there we are having the three layers. So if we are considering this is the brick, then we are having this is the plaster and this side plaster. Okay, now actually this Fourier's law is applicable only when we are knowing the surface temperature. Okay, so if here we are having T1 and here we are having T2, here T2, then across this wall we can calculate the value of Q by using Fourier's law. But for this composite structure, it's difficult to calculate that value of Q by using this law. That's why we are using the electrical analogy. Now similarly, in electrical system, we are having one pipe, and on that pipe we are having different layers. Okay, for example, electric wire. Okay, electric wire is insulated by some another material. Also, hot pipes through which hot fluid is flowing. In that case, to avoid the heat loss, we are using the insulation. Okay, so in that case also, it is difficult to calculate the value of Q. So we are using the electrical analogy. Okay, clear? So why we are using electrical analogy in heat conduction? Because by using simple formula, we can calculate value of Q for the composite structures. That's why we needed the electrical analogy. Okay. Next. So how electrical analogy used? So basically, first we will see the electrical system. Now electrical system here, this is our conductor. Okay. If the two nodes of the conductor are attached with the battery, then let us say this is our battery. It is as delta V. Okay. So if any conductor attached with the battery plus minus, then current I will be flow inside the system from positive to negative. Okay, now due to that current, one resistance R is generated inside the conductor. Now that value of current or resistance R, we can have current I is equals to delta V divided by R. Okay, so it is standard formula. So I is equals to delta V by R in simple case. Now in heat conduction equation or in heat conduction system, let us say we are having one slab. Now that slab is kept at a two temperature. Here we are having T1 and here T2. Okay. Now this we can say that T1 we can put T1 here, sorry, we can put T1 here and T2 here. Okay, now we are knowing that delta V means what? It is potential difference. Here we are having T1, T2, so this is the temperature difference. Okay, or we can say delta T. Now due to the temperature difference, heat is flowing inside the system. So Q is flowing inside the system. Now in electric system, due to potential difference, current I is flowing. In conduction system, due to temperature difference, Q is flowing. So as in electrical system resistance R is generated, then some sort of resistance is generated inside the thermal system. So here also we are having one R. Now this R is known as RTH, that is R thermal. Okay, so similar to this equation, we can have equation here I, so here we are having Q is equals to delta V means delta T divided by, here we are having R electrical resistance, so here we are having R thermal. Okay, so in simple case, we can compare this electrical system with the heat conduction system. Okay, now we can take advantage of this electrical system is that if we are using conductors are in series, 2 to 3 conductors are in series. So this is one, let us say here we are having another one, here we are having another one. So these are the three conductors in series. So we are having 3 resistors. So this is R1, R2, R3. Okay, R2 and R3. Okay, so in this case, our I becomes I is equals to delta V divided by, as the resistors are in series, so R1 plus R2 plus R3. So similarly, if we are having plaster, that is extra layer on our wall, on our slab, and another extra layer, so similarly R thermal 1, R thermal 2, R thermal 3 is generated. Now as this is in series, so we are taking R1 plus R2 plus R3. So here also we can take in thermal system RTH1 plus RTH2 plus RTH3 equals to R equivalent. So due to this, using this analogy, our problem becomes too much simplified and we can easily solve the problem. Okay. The next, we'll delete all this. So we are having the base equation Q is equals to T1 minus T2 RTH. In previous slide, we see that how that RTH comes. Now for composite wall, we are having so we have to just compare this equation with standard equation. After comparing, just we have to take, already we are in B ideal motor, so take that K towards denominator and we are getting Q is equals to T1 minus T2 B by K. So for slab, so this is nothing but for slab RTH, the thermal resistance equals to B by K. Now, similarly for composite pipe, or infinite long hollow cylinder, we are having Q is equals to 2 pi KL T1 minus T2 divided by ln of R1 by R2. So just take that 2 pi KL towards the denominator. So comparing with this equation, we are getting RTH equals to ln of R1 by R2 2 pi K. Okay, so in analogy for solving complicated problems, we are using RTH for slab equals to B by K, and RTH for composite pipe or infinite long hollow cylinder, RTH equals to ln of R1 by R2 2 by K. Okay, so next we will see we are having 2 types of resistance. One is series resistance and parallel resistance. Now if we are having the simple wall, that is wall of our home, So we are having inside plaster, then middle layer is bricks, and outer layer is plaster. So in such a case, we will draw. For such a case, we will draw the structure. So that blue one is the plaster. That red zone shows the bricks, and again that blue zone is the plaster. So let's have its thermal conductivity K1, K2 and K3. Okay. Now let us say inside air is at 100 degrees centigrade and outside air is at the atmosphere. So inside air, that is T1, it is hot, and outside air is T2. Now due to air is present around the wall, inside and outside, that's why there is a convection. So convective transfer coefficient H1 and H2 is also present there. Okay. Now remember that number of coefficients are equals to the number of resistance. So here we are having coefficients 1, 2, 3, 4 and 5. So we are having 5 resistance R1, R2, R3, R4, R5. Okay. Now while also solving the problem, we have to construct that electrical circuit equivalent to our problem. Okay. Now as that heat is transferred from that T1 temperature, so first by convection, then conduction, then conduction, then conduction, again by convection. So this process is the series process. That's why, or just we can see inside the figure, this is the series process. So we can having R1, R2, R3, R4, R5 which are in the series. Okay, so how we will get equivalent thermal resistance? So just add. So for RTH equals to R1 plus R2 plus R3 plus R4 plus R5. And its values are, for convection, it is 1 by H into A. So here we are having H1, so it is 1 by H1A. Then here we have thickness B1, so R2 equals to B1 by K1, B1 by K1A. A is the area of this space. Okay, this is the area A. Okay, similarly then for R3 it is B2 by K2A. For R4 it is B3 by K3A. And for last one, for this H2, 1 by H2A. Okay, it's quite simple. So we are getting heat flow Q is equals to T1 minus T2 divided by RTH. So whatever value of RTH we obtain from this equation, you can just put and find the value of Q. Okay, so it is quite simple. Okay, now if resistance are in parallel, okay, so we are having the wall, or we can say compartments made in the offices. Okay, so at bottom layer they are having aluminum foils, and in middle they are having glass, and from upper side there also the frame of aluminum. Okay, now due to this, the inside temperature for that glass and aluminum are the same. So similarly, let's say that red one it is the glass, and bottom one it is the aluminum, and upper one is also aluminum frame. Okay, so due to that, the inside temperature is kept at T1. Okay, now here we are not having we are not taking the temperature of the air, we are taking directly temperature of the surface. Okay, now inside surface temperature of that aluminum frame, glass and upper aluminum frame is T1, and assume it is equals to, let us say, 70 degrees centigrade. Similarly, outside frame surface, that is again aluminum, glass and upper aluminum, it is at the temperature T2, so let us say atmospheric temperature 25 degrees centigrade. Now due to that temperature difference, we are getting the heat flow. Now as the surfaces are in parallel, that's why we will show the resistance in electrical circuit parallel. So here we are in R1, R2, R3. Here also we are in area common. This is common area A, that is perpendicular area to the heat flow. Heat flow, we are in direction of heat flow Q, like this. Okay. Now depending on this figure, we are having, that is all resistance are in parallel. That's why equivalent resistance equals to 1 divided by RTH equals to 1 divided by R1 plus 1 divided by R2 plus 1 divided by R3. So we will put the values. We will get the value of, that is, which is equals to 1 divided by RTH. Okay. Now to get exact R equivalent, so just take its reciprocal, and here we are getting the value of RTH. Sorry. Okay. So just take its reciprocal and we are getting the value of RTH, and by putting this value inside this equation we will get the value of heat Q. Okay, now it is quite simple.